In the last lecture, we observed that finding 4 bases, the basis for the 4 subspaces of A involves eigenvalues and eigenvectors. We said that this is going to involve the notion of the eigenvalues and eigenvectors if you want to find suitable basis which will solve our problems. We found that the problem of diagonalization we said that this is also going to involve eigenvalues and eigenvectors. This is the main problem that introduces the notion of eigenvalues and eigenvectors, and so we started looking at this problem of diagonalization. What is the problem? The problem is given a matrix A which is real n by n, can we find a invertible matrix P such that P inverse A P is a diagonal matrix. We found that this problem, such a question arises from the type of change of variables that we want to introduce in a system of equations in order to reduce it to a diagonal system or an easy system. So, the question is, can we find a matrix P which converts A to a diagonal matrix by this transformation P inverse A P. Now, let us look at some examples. First example, let us take the 2 by 2 matrix 0 1 1 0. It is a 2 by 2 matrix. So, it is a real 2 by 2 matrix. Now, consider this matrix P, we shall see later how we found this P 1 1 1 minus 1. This is clearly in R 2 2. So, this is again a real matrix 2 by 2, and the determinant of P is minus 2, which is not 0, and you have learnt in earlier classes that the matrix P is invertible if the determinant is not 0, hence P is invertible. And for 2 by 2 matrices, the inverse is easy to find. The inverse is 1 over the determinant, the interchange the diagonals and then change the sign of the off diagonals. So, the inverse of a 2 by 2 matrix is 1 by the determinant, the diagonals interchanged and the off diagonal signs changed. So, this is the matrix P inverse and we see that let us calculate A P. A is the matrix 0 1 1 0 and P is the matrix 1 1 1 minus 1. When we take the product, we get 1 minus 1 1 1, which we can write as 1 1 1 minus 1 into the diagonal matrix 1 0 0 minus 1. Therefore, this matrix 1 minus 1 1 1 can be written as the product of these two matrices. It is easy to check, when you take the product of these two matrices you get this matrix, but 1 1 1 minus 1 was P and we will call this diagonal matrix as D, where D is the diagonal matrix 0 1 minus 1. And since P was invertible, we get P inverse A P, taking the P to the other side, D a diagonal matrix. Hence, we have an example here of a 2 by 2 real matrix A for which we are able to find a P which is invertible and P inverse A P is diagonal. Okay. So, thus there exists, this is the question we raised, whether we can find such a P. In this example, we have found such a P. There exists an invertible P which is in R 2 by 2 matrix, such that P inverse A P is a diagonal matrix. So, we get the answer in the affirmative for this matrix. Our question was, can we find a P such that P inverse A P is diagonal matrix, and in this example for this matrix you have got the answer as yes. Now, let us look at another example. Example 2, let us consider A to be the matrix 0 1 0 0. Now, we will show that there is no such P. We will show this is a matrix real. We will show that there is no matrix P in R 2 which is invertible and such that P inverse A P is a diagonal matrix. And we will show this by contradiction. We shall show this by contradiction. What do we mean by that? That is, we assume that there exists such a P and show that that leads to a contradiction. So, suppose there exists an invertible P in R 2 such that P inverse A P is diagonal. Suppose it is possible, we shall show that leads to a contradiction. So, if that is the case, we have P inverse A P is equal to a diagonal matrix. Let us call it as D 1 D 2 0 0. Suppose P inverse A P is a diagonal matrix, that says A is P times the diagonal matrix times P inverse. By pre multiplying by P and post multiplying by P inverse both sides, we get A equal to this matrix. If this is so, we get A squared is equal to P into D 1 0 0 D 2 P inverse, that is A has to be multiplied by A again. A into A is A squared, which is this. But now, P inverse P is identity. So, this becomes P into D 1 0 0 D 2 into D 1 0 0 D 2 into P inverse. This is because the middle P inverse P is an identity matrix. But now, it is easy to multiply the diagonal matrices in the middle to get D 1 squared 0 0 D 2 squared P inverse. So, therefore, we get A squared and hence A squared is this. So, let us call this as 1. On the other hand, we are given the matrix A, let us find what A squared is. A squared is A into A, this was the matrix A. So, we are trying to find the A squared is A into A. When we multiply these two matrices, we get the 0 matrix. Therefore, now if we compare 1 and 2, we see that the right hand side here must be equal to the 0 matrix. So, we get P into d1 squared 0, 0 t2 squared into P inverse is the 0 matrix. This is by 1 and 2. Now, we again pre multiply by P inverse and post multiply by P, we get T1 squared 0 D2 squared is equal to P inverse into 0 0 0 into P, but 0 multiplying any matrix is 0. So, we get D1 squared 0 D2 squared is 0 0 0, and therefore, it implies D1 is 0 and D2 is 0, which means the matrix D we got here, we got this matrix D, let us suppose I call this matrix as D, D must be the 0 matrix, and hence we get D equal to 0 matrix, and therefore, P inverse A P equal to D implies P inverse A P is the 0 matrix, and once again taking the P's to the other side, we get A is the 0 by 0 matrix. But that is a contradiction, because we are given that A is the matrix 0 1 1 0 1 0 0, contradiction, because A equal to 0 1 0 0, which is not the 0 matrix. And therefore, our assumption that suppose there exists such a P, let us, we started with the assumption that suppose there exists an invertible P such that P inverse A P is diagonal, led us to a contradiction, and hence that assumption must be wrong. Therefore, there does not exist any invertible P in 2 by 2 real matrices such that P inverse A P is a diagonal matrix. So, thus we have two examples. In the example 1, we were able to find a matrix P such that P inverse A P is diagonal. In example 2, we showed that there cannot be any such matrix, and therefore, the possibilities are both. There are cases where we can find a P such that P inverse A P is diagonal. There are cases where P cannot be found, and therefore, it becomes necessary for us to classify those matrices for which P inverse A P is diagonal, and those matrices for which we cannot find P inverse A P as diagonal. Hence, we have two examples, in one of which we were able to find a P such that P inverse A P is diagonal, and in the other there does not exist any such P. So, therefore, it becomes necessary for us to bring it some tests which would decide whether we will be able to find a P or we will not be able to find a P. Hence, it becomes necessary to look for some conditions which guarantee, which assure that such a P exists. So, we shall look for such conditions. So, we will use a terminology now. So, we will give a definition. A real matrix n by n is said to be diagonalizable over R if there exists an invertible P. If there exists an invertible P in n by n real matrix, that is what is meant by over R, that the P that we are looking for is a real matrix such that P inverse A P is a diagonal matrix. So, what it means is that the example 1, the matrix A in example 1 is diagonalizable over R because we have found such a P, and the matrix A in example 2 is not diagonalizable over R because we are not able to find such a P, is not diagonalizable. We said that there cannot exist such a P, and therefore, it is not diagonalizable. So, instead of writing there exists a P such that P inverse A P etcetera, we simply say diagonalizable over R. So, a matrix A is diagonalizable over R if there exists a P such that P inverse A P is a diagonal matrix. As observed, the matrix of example 1 is diagonalizable over R, the matrix of example 2 is not diagonalizable over R. It is therefore becomes necessary for us to derive some conditions under which we can say if A satisfies these conditions, we are guaranteed that A is diagonalizable over R, and if A does not satisfy these conditions, then A is not diagonalizable over R. So, this should be some kind of a litmus test for diagonalizability over R of a matrix. So, we shall start looking, searching, hunting for such matrices, for such conditions. Now, the first thing to do is look at a matrix which we know is diagonalizable and see how it looks, what is it made up of, or what makes it diagonalizable, and then from that learn what makes things work as far as diagonalizability is concerned. So, let us start. Let us first consider a matrix A which is real n by n, which is diagonalizable over R. Which is diagonalizable over R. Okay. Now, what does this mean? By definition then, by definition this means there is an invertible P which is in real n cross n such that P inverse A P is equal to D, a diagonal matrix. Now, let us write this in a different form. This implies A P is P D. Multiplying both sides on the left by P, we get P P inverse A P, which is A P, and right side becomes P D. Now, let us look at each one of these sides, left side and right side carefully. Now, P is a matrix, it is an n by n matrix, and therefore, it has n columns. Each column has n rows. So, each column is an n by 1 vector. Each column therefore, belongs to R n. So, P is an n by n matrix, it is real. Therefore, each column of P is an n by 1 matrix, that is P, each column is a vector n component. Now, let us denote these columns as P 1, P 2, P n. So, P 1 will therefore be the first column, it will have n entries, P 2 is the second column, it will have n entries, P n it will have n column n entries as a column vector. Now, then P can be written as in column notation P, its first column is P 1, second column is P 2 and the nth column is P n. So, therefore, with this notation let us go back to this equation 1, which says A p equal to P d. So, therefore, the left hand side of 1 becomes A p, which is now equal to A into P 1, P 2, P n. Now, when you multiply the matrix, it just becomes A P 1. The first column of this product is obtained by multiplying the matrix A by the first column of P. Then the second column is obtained by multiplying the matrix by the second column of P and A P n. This is the left hand side of the equation. Similarly, the RHS, the right hand side of 1 becomes, so let us call this as RHS. This is this is the LHS. So, let us call this the left hand side. Now, let us look at the RHS. The RHS is P d. Now, P is again written in column notations and D, let the diagonal matrix be lambda 1, lambda 2, lambda n 0. If when I multiply this in block notation, this becomes lambda 1 P 1, lambda 2 P 2 and so on lambda n P n. So, this is the RHS and therefore, equating the LHS to the RHS. So, therefore, LHS equal to RHS implies this matrix A P 1, A P 2, A P n must be equal to the matrix lambda 1 P 1, lambda n P n. That means, the first column on the left hand side is A P 1 and the first column on the right hand side is lambda 1 P 1. Since the two matrices on both sides are equal, the corresponding columns must be equal and therefore, we get A P 1 equal to lambda 1 P 1, A P 2 equal to lambda 2 P 2 and so on A P n is lambda n P n. Now, let us go back, this lambda 1, lambda 2, lambda n are the entries in the real diagonal matrix D and therefore, lambda 1, lambda 2, lambda n are scalars. So, lambda 1, lambda 2, lambda n are real numbers. Recall that the columns are all in R n, they are all column vectors and they have n components. So, thus we get A P 1 equal to lambda 1 P 1, A P 2 equal to lambda 2 P 2, A P n equal to lambda n P n. Now, therefore, we have found n scalars lambda 1, lambda 2, lambda n and n vectors P 1, P 2, P n such that A P 1 is lambda 1 P n and so on and so forth. Not only that, these vectors P 1, P 2, P n must be linearly independent because they form the columns of an invertible matrix. Therefore, the rank must be n. Hence, we get that implies there exists n real numbers lambda 1, lambda 2, lambda n. Now, notice that these are only the entries in the diagonal matrix. There is no compulsion that the same entry should not repeat or anything like that. So, these need not be necessarily distinct. They may be different numbers or some numbers may be repeating, it does not matter, they are all real numbers, and n linearly independent vectors p 1, p 2, p n in R n such that a p j equal to lambda j p j 1 less than or equal to j less than or equal to n. So, what is our conclusion therefore? If you assumed or if you know that A is a diagonalizable matrix, if A was, we started off with A as a diagonalizable matrix and we are able to conclude that this would force the existence of n numbers lambda 1, lambda 2, lambda n, n real numbers lambda 1, lambda 2, lambda n, and n linearly independent vectors p 1, p 2, p n, that this exists. So, what is our conclusion? Let us call this as conclusion 1. A or n cross n, n by n matrix real is diagonalizable over R implies there exists n real numbers lambda 1, lambda 2, lambda n not necessarily distinct such that and n linearly independent vectors p 1, p 2, p n in R n such that a p j equal to lambda j p j for 1 less than or equal to j less than or equal to n. Let us illustrate the above calculation. So, look illustration for a 2 by 2 matrix. Just to see what these calculations mean. So, suppose I have a 2 by 2 matrix A, B, C, D belonging to R 2 cross 2 and A is diagonalizable over R. What does that mean? This implies there exists P, let us call it as P Q R S belonging to R 2 2, P invertible. What does P invertible mean? The determinant is not 0. So, P R minus Q S is not equal to 0 such that P inverse A P is equal to a diagonal matrix. Let us call that as lambda 1, lambda 2. What does this mean? This says A P equal to P D. Now, what is A P now? Left hand side, A is A, B, C, D, P is P, Q, R, S, which is equal to A P plus B R, A Q plus B S, C P plus D R, C Q plus D S. Now, let us look at our column notation. We have P 1, the first column of P 1 is P R, P 2 is Q S. So, what is A P 1? AP1 is ABCD into PR, which is AP plus BR CP plus DR. This is the first column of the product. This is what we meant by saying the first column of the product will be AP1. Okay. So, this is what AP1 is. Similarly, AP2 is ABCD into QS, which is AQ plus BS CQ plus DS, which is the second column of this LHS. Therefore, LHS is the matrix AP1 AP2. The first column is AP1 and the second column is AP2. What is the RHS? RHS is PD. What is P? PQRS, and D is lambda 1 0 0 lambda 2, and the product is going to be lambda 1 P 0 the lambda 1 P lambda Q 2 Q lambda 1 R lambda 2 S. Now, what is the first column of this? The first column is lambda 1 into PR, which is just lambda 1 P1. Second column is lambda 2 into QS, which is just lambda 2 into P2. So, therefore, RHS is nothing but the matrix lambda 1 P1 lambda 2 P2. Now, LHS was, as we found, AP1 AP2, and therefore, equating the LHS. So, LHS equal to RHS gives us the corresponding columns are equal. So, AP1 equal to lambda 1 P1, AP2 equal to lambda 2 P2. Now, this is what we looked at in the general case. In the n by n matrix case, it is not just one lambda 1 and lambda 2 and P1 and P2. We get lambda 1, lambda 2 and lambda n real numbers P1, P2, Pn vectors such that APJ is equal to lambda JPJ. Let us look at even a specific example. Look at a very specific example. So, recall example 1, we had A was 0 1 1 0. We found P equal to 1 1 1 minus 1 and P inverse AP is equal to 1 0 0 minus 1. This is my diagonal matrix. So, in this case my P1 is the first column of P, P2 is the second column of P, my lambda 1 is the first entry in the diagonal matrix, lambda 2 is the second entry in the diagonal matrix. Check AP1 is equal to 0 1 1 0 into 1 1, which is 1 1, which is lambda 1 times P1, which is lambda 1 times P1. AP2 is 0 1 1 0, P2 is 1 minus 1, it will be minus 1 1, which is minus 1 times 1 minus 1, which is minus 1 times P2, which is lambda 2 times P2. So, AP1 is lambda 1 P1, AP2 is lambda 2 P2. So, whenever you have diagonalizability, you are assured of these n numbers lambda 1, lambda 2, lambda n and the n linearly independent vectors P1, P2, P3 such that this APJ is equal to lambda. So, this is the important thing. If A is diagonalizable over R, then there exists n scalars, real numbers lambda 1, lambda 2, lambda 3, lambda n, and n linearly independent eigenvectors p1, p2, pn such that APJ is equal to lambda j pj. Conversely, now look at this example by the way that we considered this specific example of this. Here you see that this p1 and p2 we got are linearly independent also. Okay. So, now let us look at converse. So, now we have found that the moment I have a diagonalizable matrix, these numbers and scalars, these vectors will fall apart. They must exist inside that matrix, somehow coded. We should find, we will be able to find these numbers and the vectors from the matrix A. Conversely, we will now see if I am already provided these numbers and the vectors, then the matrix A must necessarily be diagonalizable. Conversely, let A belong to the real n by n matrix class is such that, let this be such that there exists n real numbers. Previously we assumed diagonalizability and proved the existence of these numbers. Now we are assuming the existence of these numbers lambda 1, lambda 2, lambda n, not necessarily distinct, and n linearly independent vectors p 1, n linearly independent vectors p 1, p 2, p n in R n such that A p j equal to lambda j p j for 1 less than equal to j less than equal to 1. Now, in the previous case we assumed diagonalizability and we arrived at the existence of these numbers and the scalars. Now, we are assuming the existence of these numbers and the vectors and we are going to prove that A is diagonalizable. This implies, so now let P be the matrix whose first column is this P 1, second column is P 2 and the nth column is P n. So, now we construct this matrix P. Once we know that these n vectors are there, we are given there exist these n linearly independent vectors, we construct this matrix P, and since these are all linearly independent, P is in R n by n invertible because columns are linearly independent. So, we have an invertible matrix. Then what is AP? AP is equal to then AP1, P2, Pn. As observed earlier, this product will be AP1, AP2, APn, but we are given that AP1 is lambda 1 P1, AP2 is lambda 2 P2, lambda n Pn, that is given to us. So, this says star by star, and this product as before can be written as P1, P2, Pn into the diagonal matrix lambda 1, lambda 2, lambda n, and which is P times the diagonal matrix. This matrix is what I call as D. So, AP equal to PD, which implies P inverse AP is equal to D, a diagonal matrix. So, therefore, the moment that these scalars and vectors are given, we are able to construct a real matrix P so that P inverse AP is diagonal, which means A is diagonalizable. So, now we now call these conditions as C, this whole set of conditions as C. What are those whole set of conditions? There are n real numbers, n linearly independent vectors such that A p j is equal to lambda j p g. What we have seen now is C implies A is diagonalizable, and what we saw earlier was this is conclusion 2. What we saw, the conclusion 1 was nothing but A is diagonalizable implies condition C, and therefore, combining the two we get the theorem A belonging to R n n. So, A is a real n by n matrix is diagonalizable over R, this diagonalizability is over R, is diagonalizable over R if and only if C holds, that is there exists, I will repeatedly write this, n real numbers lambda 1, lambda 2, lambda n in R not necessarily distinct and n linearly independent vectors p 1, p 2, p n belonging to R n such that A p j is equal to lambda j p j for 1 less than j less than equal to. So, therefore, we now have a criterion for a matrix A, real matrix A to be diagonalizable over R. The only problem therefore is, how do I find these numbers lambda 1, lambda 2, lambda n? How do I find whether there exist these numbers? Even if I find these numbers, how do I find whether there exists such vectors p 1, p 2, p n? And even if I prove that there exists such p 1, p 2, n, how do I find these vectors p 1? So, how do I compute? Where do I look for these scalars lambda 1, lambda 2, lambda n, and where do I look for these vectors p 1, p 2, p n? Now, this leads us now to the formal definition of eigenvalues and eigenvectors. If you look at what we are looking for are vectors p j of the type p j, which are such that when they are acted upon by the matrix A, that is A times p j, they are very firm, they remain in the p j direction only thing there may be a scaling factor lambda j. In other words, the direction remains invariant under A. So, p 1, p 2, p j tell us n directions which remain unchanged when acted upon by A. They remain the same direction, but the vectors may change in their length. The magnitude or the scaling factor lambda j may come into the picture. So, therefore, we are looking for vectors which are invariant in direction under the action of A. This leads us to the notion of the eigenvalues and eigenvectors. So, definition: A is an n by n matrix a real number lambda is said to be an eigenvalue or sometimes also referred to as characteristic value . Characteristic value. So, either an eigen, whichever way you want to use it, a real number lambda is said to be an eigenvalue of the matrix A if there exists a non-zero vector phi in R n such that A phi equal to lambda phi. That is invariant. This is what we are looking at. Phi remains in the same direction as phi. So, non-zero vector phi in R n such that A phi equal to lambda phi. In such a case, phi is called an eigenvector or again characteristic vector of A, the matrix A corresponding, it is invariant and the scaling factor is lambda. So, corresponding to the eigenvalue lambda. And this pair lambda phi is called an eigenpair or a characteristic pair or characteristic pair. Now, if we look back to our criteria for the diagonalizability, we are looking for n vectors p 1, p 2, p n such that a p j is lambda j p j, and therefore, we are looking these numbers lambda 1, lambda 2, lambda n must be eigenvalues, p 1, p 2, p n must be eigenvectors. Not only that, since we want p 1, p 2, p n, we want them to be linearly independent eigenvectors. So, by the theorem now can be written as, hence by our theorem we get, in fact, the theorem can be rewritten in this language as follows: A belonging to R n n, that is A is the real n by n matrix, is diagonalizable over R if and only if there exist n eigenpairs lambda 1 phi 1, may use the same notation as before, lambda 1 phi 1, lambda 2 phi 2, etc., lambda n phi n, where phi 1, phi 2, phi n are linearly independent. Instead of p 1, p 2, p n, now I am calling them phi 1, phi 2, phi n. So, therefore, diagonalizability demands that you find n eigenpairs. If you want to diagonalize a matrix A, you find n eigenpairs in such a way that the eigenvectors coming out in these eigenpairs, the phi 1, phi 2, phi n are all linearly independent. So, the search should be for these n eigenpairs. That is going to be our main search in diagonalizability. Can we find these pairs? Where do I search? So, where do we search for these eigenpairs? And that is the main chapter of eigenvalues and eigenvectors. So, this leads us to the analysis of eigenpairs, eigenvalues and eigenvectors. This is one of the most important chapters in linear algebra. this notion of eigenvalues and eigenvectors, and in fact, the notion of eigenvalues and eigenvectors with respect to any transformation are going to play very crucial role in the structure analysis of these transformations, in particular with respect to matrices. So, now our analysis should be with respect to these eigenvalues and eigenvectors. What should be our strategy? How is it going to be our strategy? We have to find the pairs lambda and phi. If we have to find the pairs lambda and phi, we have to find those numbers lambda and then corresponding to those the vectors phi. Now, suppose we have found the numbers lambda. So, suppose we have found an eigenvalue lambda, then we seek phi such that a phi equal to lambda phi, and this boils down to looking at a minus lambda I phi equal to theta n, or if we call that matrix as a lambda is a minus lambda I, then it boils down to finding the homogeneous solution for homogeneous. So, therefore, we are looking for solution for homogeneous system corresponding to a lambda. Therefore, that is a fairly easy job. We have seen how to treat homogeneous systems. So, if we know an eigenvalue, there seems to be some hope of finding a pair eigenvector for that. So, therefore, there is hope for us to find at least the phi's in some sense the moment we know the eigenvalue. There is a chance because we have to solve homogeneous system. So, our primary, so the knowing eigenvalue lambda, there is a chance of finding corresponding eigenvector by solving the homogeneous system a lambda phi equal to theta n, where a lambda equal to a minus lambda. So, therefore, our primary search should be for the eigenvalues. So, our primary search begins with the search for the eigenvalues of E. Therefore, our next study will be, given a matrix A, where do I look for eigenvalues? I know that the eigenvalues must be real numbers. So, I must be looking for the eigenvalues among the real numbers, but there are infinite number of real numbers. Where do I go and search for them? So, I must narrow down my search, but if my search is in an infinite set, it is a hopeless task. We cannot go on searching every one of those fellows and are you an eigenvalue or are you an eigenvalue. We can't go on checking every real number and check whether it is an eigenvalue. Even if we do not check in real numbers, if we narrow down the search to an infinite subset of the real numbers, then again the problem is that we cannot search one by one in an infinite set of real numbers. So, it is again a hopeless task. So, therefore, somehow or the other we have to reduce and focus our search using the matrix A to a finite search. Somehow we must look among, because after all we are looking for a finite number, this must be somewhere scattered. So, we must somehow or the other look in a finite set of numbers and look for the eigenvalues within that finite set. So, our focus will be to reduce the search of the eigenvalues to a search in a finite set of numbers. And so, that will be our primary concern in the next chapter, to look for the eigenvalues of a given n by n matrix.